My name is Brendan Paget, and I'm here to talk to you about significant figures. So I know that a lot of students in their first year kind of have difficulties understanding and adapting to significant figures, and hopefully this presentation and video will help you out for your exam, midterm, and your lab assignments. So, first of all, why significant figures and why are they important? Significant figures are used to distinguish between more and less precise measurements, and it ensures results are accurately represented while keeping the accuracy of all instruments in mind. So in the lab, you're going to be using a lot of different instruments, and all these instruments are going to have different accuracy with different decimal places. So it's in our best interest to make sure that we have a reliable and trustworthy answer while keeping in all of the instruments in our mind. So, firstly, there are 4 general rules for counting significant figures. These rules are very, very important for your understanding and your foundation to answering different math questions that involve significant figures. So please make sure that you have these 4 rules down before continuing on to the different calculation examples. So the first rule is the easiest rule to understand. All non-zero figures are significant. That means that any sort of number or digit that is in the number will be significant as long as it's non-zero. So a number like 28.5 will have 3 significant figures, 1, 2, and 3. 92.17352 will have 7 significant figures as these are all different digits, and each digit would be significant. Number like 7 with a decimal place will have 1 significant figure. So hopefully you have this down. It's very easy to understand and apply. For the second rule, all zeros located between non-zero figures are significant. So this is also very easy to understand, as a zero that's in between 2 non-zero digits will be considered as significant. So 205.8 will have 4 significant figures, as you have 2, 0, 5, and 8. 91.000034, these 4 zeros are also considered significant, so all these digits are significant, resulting in 8. 890.306 has 6 significant figures, as these 2 zeros are also significant, and you have 8, 9, 0, 3, 0, and 6 as all significant figures. So hopefully you guys understand this as well. Moving on to rule number 3. When there is a decimal place, all zeros to the right of non-zero figures are significant. So a number like 700.0, this 0 would be recorded, and that means that it is significant since there is a digit to the left that is a non-zero. So you have 1, 2, 3, and 4 significant figures. For 21.8050, you have 6 significant figures, so you have 1, 2, 3, 4, 5, and 6. And for 1.002, it has 4 significant figures, so 1, 2, 3, and 4. So this number, 21.8050, is a number that you could see on an analytical balance, for example, and it could result in this last digit being a 0. And since you would write this down, this would be known as a significant figure. Okay, so all of these numbers in 21.8050 would be significant. Rule number 4, this is where the students get kind of messed up a little bit, and it can be a little difficult. So the rule states zeros to the left of the first non-zero figure are not significant. So these are for numbers that are between -1 and 1. So any number that starts with a 0, or any decimal formed number that starts with a 0. So this example here, 0.000321, has 3 significant figures. It has a 3, has a 2, and has a 1. So these 3 are significant. These 4 zeros are not significant. These are just placeholders, okay? So since there's a 0 before the decimal place, that means that all of these, until the first non-zero digit, will be not significant. An example like 0.12 only has 2 significant figures. And a number like 0.002 will only have 1 significant figure. So please make sure that you have this down, okay? Because this is one of the most important rules, because there's a lot of small numbers that we use in chemistry, and we need to make sure that we have that correct significant figures. Okay, so this is going to be a quick practice and discussion about 0.003501 versus 1.003501. So these are essentially the same numbers, except this one has a 1 before the decimal, this one has a 0 before the decimal. So if we go back to rule number 4, this is where this number applies to. So these 3 zeros are not going to be significant. You'll only have 3, 5, 0, and 1 as significant figures, which means that you have 4 sig figs. This number, 1.003501, these have a number right before the decimal place, and it has 2 whole digits on either side of the zeros. So that means that all of these numbers within this whole number will be significant. So you have 1.003501 will have 7 significant figures. So if you have any questions about this, please type in the comments, and I can clarify it for you down there. So these 4 steps are the foundation for determining the significant figures. As long as you can do this, you can then apply it to the rules for operations. So it can be for multiplication, division, addition, subtraction, and also logarithms. So we're going to start by talking about multiplication and division. So with this, the answer must contain the same number of significant figures as the measured number with the fewest significant figures. For example, this equation here, so 71.2 times 871.9, would result in a number of 62,079.28. Okay, but we need to make sure that we have the correct number of sig figs for this answer. So we start by analyzing the question, and we see how many sig figs are in each number. So 71.2 has 3 sig figs, and 871.9 has 4 sig figs. Going back to the definition, it needs to go to the fewest significant figures. So our answer here needs to have 3 significant figures, because this is the fewest in the equation. So answer with 3 sig figs would then be 6.21 times 10 to the 4. So we rounded this number, so this 7 would go up to becoming a 1, and our answer would be 6.21 times 10 to the 4, which has 3 sig figs. Okay, addition and subtraction. This is the difficult operations that people struggle with. So the definition states the answer must contain the same number of digits to the right of the decimal place as the measured number with the fewest digits to the right of the decimal point. Okay, so for example, if we're adding these 3 numbers together, we have 50.1, 200.15, 200.22222. We would get an answer of 450.47222. We need to look at the smallest decimal place, which would be 50.1. There's nothing on the other side of that. So this only has 1 decimal place, which means that we need to look at our answer and only have 1 decimal place. Okay? That means that our answer would be 450.5, as we rounded the 7 up to a 5 here. But it's good to keep in mind that this is now 4 sig figs. Even though the question had 3 sig figs as 50.1, our answer has 4 sig figs because it goes down to the decimal place. Alright, so you need to make sure that the decimal place is what's important for addition and subtraction. So what you can do is just align up the decimals for each number, find the smallest one, carry it down, and then round it to whatever that smallest decimal is. Okay, logarithms. So when you're logging a number, such as 8.6 times 10 to the 4, you get an answer kind of like this. You have 4.9344 with a bunch of other decimal points afterwards. So we need to make sure that we have this answer to the correct number of significant figures. But how do we do that? The first step is to know that a logarithm answer is broken up into 2 pieces. The first piece, which is the number before the decimal place, is known as the characteristic. And the numbers after the decimal place is known as the mantissa. and the mantissa is what we're going to be using as our significant digits. So, the definition for this is the number of sig figs in the value that will be logged will be equal to the mantissa. Okay? So, logging 8.6 times 10 to the 4 has 2 sig figs. So, when you have 2 sig figs, and going back to the definition, that means that the mantissa needs to have 2 sig figs. So, going to our answer, the mantissa, which is the numbers after the decimal place, is only 2. So, our answer would be 4.93. Looking at ANT logarithms, it's very similar to logarithms, just the opposite function. So for example, if we're taking 10 to the power of 4.9344, we would get an answer of 85980.50666661, which is a long number with a lot of different significant figures. But that's not correct, right? So we need to look at the mantissa of our number that we are anti-logging. And so we can see that there are 4 digits within this number. That means our answer needs to have 4 significant figures. So we have 8.598 times 10 to the 4. Perfect. So I really hope that this video helped you understand significant figures. And if you have any questions, please type them in the comments and I'll do my best to reply to them. But thank you so much for watching. Please like, subscribe, and I'll see you guys next time.